Hello, and welcome to Lesson 12 of this Introduction to Probability of Wolfram. The topic for this lesson is the Bernoulli distribution. Let's begin. In Lesson 3, when I defined events, I mentioned binary sample spaces. An event on a binary sample space is called the Bernoulli trial. There's a discrete random variable associated to it, with only two outcomes. This is the Bernoulli distribution, first studied by Jacques Bernoulli in his book The Art of Conjecturing. While this is admittedly a very simple distribution, it's also arguably the cornerstone of all other discrete distributions in this course. A Bernoulli trial is usually best understood as a success or a failure event, where success and failure are mutually exclusive, it's one or the other. Success has a given probability p, and failure is the natural complement, as it has the probability 1 minus p. If you take the PDF and CDF of the distribution, the probability that x is equal to 1, that is, a success, is p, and the probability of failure, x is equal to 0, is 1 minus p. For the CDF, the function starts at x is equal to 0 with 1 minus p, and then accumulates to 1 at the value x is equal to 1, as you're adding success probability. All PDF explained in the next two chapters can be user-defined. For example, you can define the Bernoulli PDF yourself, then plot it. But it's usually better to use the built-in distribution, named Bernoulli distribution, as you see here plotting the CDF. I chose to set the plot range so that you can clearly see the absolute increase or decrease of probability. The mean is the expected success. For this distribution, you're given the expected success, p. So naturally, the mean of the probability distribution is p. What about the variance, representing variation? Well, if the probability of success is 1 or 0, then the outcome never varies. So the variance should be 0 at those points. If, however, p is equal to 0.5, like a coin flip, one would expect the most variation. If you plot the function p times 1 minus p, you get a curve that fits those requirements. And indeed, this is the variance of the Bernoulli distribution. But when is the Bernoulli distribution actually applied? Well, this distribution is more of a mathematical tool than a practical one. This distribution serves as a basis for other, more complicated distributions. So, in practice, it's formally used to make mathematical proofs and informally used to communicate the probability of an event. Now, we'll go through different things that you usually do with a probability distribution. At first, it may seem excessive to go through all that terminology for such a simple distribution. But trust me, soon enough, these steps will be crucial to your understanding. Just try to keep in mind how you would use those distributions explained to you. So first, you can use the probability function. Let's say a given surgery has a 0.9 probability of success. Then what's the probability it fails? You can find it by taking the probability of x equals 0, where x is the Bernoulli distribution at 0.9, and then you get the expected 0.1. Using the expectation function, you can complicate things a bit. Let's say you roll 6 fair 6-sided dice. How many ones should you expect to see? Well, intuition usually says that it's a chance 1 over 6, and if you try 6 times, then that should mean that you have at least a single 1, right? Okay, let's check that intuition. Take the expectation of 1, 2, 3, 4, 5, 6 dice, all Bernoulli distributed at 1 over 6, and indeed, on average, you get a single 1. Okay, let's say a poll finds that 3 out of every 4 citizens approve the latest decision of the mayor. How would you represent this visually? Well, you could use a bar chart, but you would need to distinguish between those that disapprove and those that approve. You can do the same with a pie chart. But again, distinguish those that disapprove and those that approve. Of course, you can simulate a Bernoulli distribution. Use random variates on the distribution of your choice and the number of samples. Using the mean function, you can compare the mean of your sample to the probability of success to check for accuracy. If you have binary data, you may also want to estimate a Bernoulli distribution. For example, load the dataset of motive failures and check status, and replace failed instances by 0 and working instances by 1. Estimate the data on the Bernoulli distribution, and plotting the data against the estimated distribution, you can confirm they correspond. In summary, a Bernoulli trial is an event with two outcomes, success or failure, where success has a probability of p and failure has a probability of 1 minus p. Use the Bernoulli distribution to calculate any Bernoulli distribution problem. In the expectation example earlier, you tossed 6 dice, so you made 6 Bernoulli trials. What happens actually when the distribution you have makes multiple Bernoulli trials? Well, that's next lesson, where we extend the Bernoulli distribution to the binomial distribution using repetition.